Hello all. In this session we will discuss about the next topic, that is multiplication. The multiplication is a complex operation than addition and subtraction. It can be performed in hardware or software. A wide variety of algorithms have been used in various computers. For simplicity, we will first see the multiplication algorithm for unsigned integer, that means positive integers, and then we will see the multiplication algorithm for signed numbers. So now let's see a usual algorithm for multiplying positive numbers by hand. So here this method is also known as a school method. So what we have learned in school, the basic multiplication operation. So here let's take one example. We have here we are taking multiplicand as 13 as a multiplicand and 11 as a multiplier. So multiplicand represent by using a letter M, multiplier represent using Q. So we are doing here M into Q. So next convert this into a binary format. So here we have got a 4-bit number. So 13 is represented as 1101 and 11 is represented as 1011. So how to do a multiplication of unsigned numbers? So here we need to check the first bit from the multiplier, that is nothing but a Q0. So if the Q0 is 1, then we need to multiply that with the multiplicand M. Okay, means we will be getting the same multiplicand. We need to write the same multiplicand in the as a partial product. So then the bit in the multiplier, that is Q1. So that is also 1. So 1 into M, so you will get the same multiplicand, but we need to shift one position to the left. Okay, so here when you write a partial product, we need to shift it right. So then the next bit, that is Q2, that is 0. So 0 means the partial product will be 0. 0 into M, that is nothing but the all the bit value will be 0 as in the partial product. Then the next bit is 1. So 1 into M, so you will get the same multiplicand value. So once it is done, we need to add these all these partial product, then we will get the product here. So this is the product. So when we convert this into a decimal value, so we will get 143. So 13 into 11, that is nothing but 143. So here this is a conversion. So we have all these values, 128 plus 8 plus 4 plus 2 plus 1. So when you add this, you will get 143. So here the product of two n-bit number is at most a 2 n-bit number. So if we are using a 2 n-bit number, so here we are using 4-bit number. So multiplicand and multiplier is also both, it's a 4-bit number. So the product will be 2 into n. So here n is 4. So 2 into 4, that is nothing, 8-bit. So the product will be a 8-bit number. Unsigned multiplication can be viewed as an addition of shifted versions of the multiplicand. So here the addition will be the product what we will get, that will be viewed as an addition of shifted versions of the multiplicand. So next we'll see one more example, that is nothing but 12 into 13. So same procedure. So multiplicand is 12, multiplier is 13. So we need to perform M into Q. So this is the binary format of this number. So if so here Q0 is 1. So we need to write the same multiplicand. So we got the partial product as 1100. Next Q1 is 0. So all the values becomes 0. Next is 1. So 1 into m, so we'll get the same multiplicand value. Again q3 is also 1, so we'll get this. When we add this value, we will get the product as 156. So m bit multiplicand into n bit multiplier, you can write it as m plus n bit product. Okay, so here both are 4, so 4 plus 4, 8 bit, or you can write it as a 2n bit product. So here we added the partial products at end. Alternative would be to add the partial products at each stage. So here we need to follow some rules to implement multiplications are, if the ith bit of the multiplier is 1, shift the multiplicand and add the shifted multiplicand to the current value of the partial product. Hand over the partial product to the next stage. Value of the partial product at the start stage is 0. Looking at these algorithms, we can note following points. The first one is like multiplication process involves generation of partial products, one for each digit in the multiplier. These partial products are then summed to produce the final product. Second one, in the binary system, the partial products are easily defined. When the multiplier bit is 0, the partial product is 0. And when the multiplier is 1, the partial product is the multiplicand value. The third one, the final product is produced by summing the partial product. So before summing the operation, each successive partial product is shifted one position to the left relative to the preceding partial product. So that is very important. So that is what we get as a partial product in each stages. The product of two n digit numbers can be accommodated in 2n digits. Okay, so that so the product of the two 4-bit numbers it fits into 8 bits product value. So next we'll discuss about a multiplication cell which is used to perform a multiplication of unsigned numbers. This diagram shows a typical multiplication cell. So here we have a full adder and one AND gate. The binary multiplication of positive operands can be implemented in a combinational two-dimensional logic array. So as shown in this diagram, the main component in each cell is a full adder. So here also we are using a full adder for the binary addition. The AND gate in each cell determines whether a multiplicand bit mj is added to the incoming partial product bit. So based on the value of the multiplier. So here we will be deciding whether we need to add the multiplicand to the partial product or not based on the multiplier bit value, that is qi. So if qi is 1, then we will be adding the multiplicand bits to the partial product. If qi is 0, then we will take the value as 0 and the previous partial product will be taken downwards. So here in each row adds the multiplicand to the incoming partial product PPI, that is nothing but a partial product. So bit of incoming partial product is represented as PPI, and the output going from this cell, that is nothing but bit of outgoing partial product, that is PPI plus 1, which is going out of the cell to the next stage. So here the multiplicand it adds the multiplicand to the incoming partial product PPI to generate the outgoing partial product PPI plus 1. If qi value is 1, so if qi value is 1, then all these things will happen. If qi value is 0, PPI, that is partial product of that ith stage, is passed vertically downward unchanged, means the value will be 0, so all the bit value will be 0. So the partial product will be vertically downward unchanged. So PP0 is all 0, so partial product becomes all 0, and PP4 is the desired product. The multiplicand is shifted left one position per row by the diagonal signal path. So in each stages, the partial product will be one bit shifted to the left. So finally, it is going to give the product of M into Q. So next we'll discuss a combinational array multiplier. So what we use in the previous procedure, what we discussed. So this is the combinational array multiplier used to perform multiplication of unsigned numbers. So here you can see we have taken multiplier and multiplicand and multiplier. So how these partial products are generated. So first what we will do, we will take the multiplier value, that is Q0. So here it is B0. So if B0, what we'll do, we will multiply this with the multiplicand, all the bits from the multiplicand value. Okay, so we'll do all the we'll consider all the multiplicand bit and we will do multiply with this A0. So that will be done with the AND gate. Okay, so that is all these things will be done with AND gate. So the truth table for AND gate is if both the values are 1, then the result will be 1. Otherwise it is 0. So here if B0 is 0, so 0 plus, if the multiplicand is 0, then obviously it is 0. If it is 1 also, it is 0. So that's why if B0 is 0, then you will be getting all the values as 0. So like this we will do for all the bits, and finally we will be getting the partial product stages. So first partial product will be getting through B0 with multiplied with all the bits from the multiplicand value. Then the next stage B1, we will take B1, multiply with all the bits of the multiplicand, then B2 with all the bits of multiplicand, then B3 with all the bits of multiplicand, and so finally by using a full adders we will be adding all these partial product values, and we will be getting final product as the results for this multiplication operation. So here the one thing we need to see here, to perform this operation or to perform this procedure, so many cells we need. So it is only for 4-bit value, so we need 16 array multiplier cell we need. Okay, only just for 4-bit value. So just imagine if it is for 16 bit, 64-bit, 128-bit or 258 bits value. So we need a huge number of this array multiplier cell. So that is one disadvantages of combinatorial array multiplier. So that's why it is not efficient. It is not a efficient multiplication method. So combinatorial array multipliers are extremely inefficient, have a high rate count for multiplying numbers of practical size such as 32-bit or 64 bits, perform only one function, namely unsigned integer product. Means we cannot use this for the negative operands. It won't work for negative integers. So it is only for a positive numbers or unsigned integer. So it improves gate efficiency by using a mixture of combinatorial array techniques and sequential techniques requiring less combinational logic. So that we will discuss in the next topic. So here this particular method, as I said, the multiplication cell is having one full adder, one AND gate. So it minimum it will introduce 2 gates delay. For each cell it will introduce 2 gates delay in the when it performs a multiplication operation. So each cell is generating 2 gates delay. Just imagine, so how much gate delays will be introduced in this overall overall multiplication operation. So that's why combinatorial array multipliers are inefficient. It is an inefficient method. So we can improve the delay gate efficiency by using mixture of combinatorial array techniques and sequential techniques. So it will reduce the gate delays, and it requires only less combinational logic gates. So as I said, this array multiplier method, it won't work for negative operands. So it will perform only on the unsigned integers. So we'll take one example here with a negative operand. So I have considered 25 into minus 25. So what we need to do, as we discussed in the previous session, so here 25, it is a positive number and the multiplier is negative. So we need to take a 2's complement here. So first we need to take plus 25, convert into 1's complement plus add 1 to it. So you will get this as a negative 25. So then we'll consider these two and we'll perform same the school method or by using this combinatorial array multipliers procedure. So when we do this multiplication, the final product will be, we will get it as 175. So but the answer is wrong. So 25 into minus 25, we should get answer as minus 625, but here what we got 175. So just convert this, you will get 175. The answer is wrong. So that's why the combinatorial array multipliers procedure, it will apply only for the unsigned integers. So to overcome all these drawbacks of combinatorial array multipliers, we have the another procedure. So that is nothing but sequential multiplication. So here recall the rule for generating partial products. If the ith bit of the multiplier is 1, add the appropriately shifted multiplicand to the current partial product. Multiplicand has been shifted left when added to the partial product. However, adding a left shifted multiplicand to an unshifted partial product is equivalent to adding an unshifted multiplicand to a right shifted partial product. So in the sequential circuit multiplier, so this is the circuit what we use for sequential circuit multiplier. The simplest way to perform multiplication is to use the adder circuitry in the ALU for a number of sequential steps. So this block diagram shows the hardware arrangement for sequential multiplication. This circuit performs multiplication by using a single n-bit adder n times to implement the spatial addition performed by the n rows of ripple carry adders. So here we use two registers A and Q, which will be combined to hold the partial product. Means in the ith stage, whatever the partial product it generates, so that will be represented by using these two registers A and Q. The final product will be nothing but the combined bits of these two registers. So initially in the first step, what we will do is we will take A value as 0 and Q registers will be having a multiplier value. Okay, so here we performs two operation, add or no add. Okay, so add or no add operation. So for that we need a one control line. So if it is a add, it has to perform a addition operation. So it will add the multiplier values with whatever values there in the register A. So this will be done by using a n-bit adder. So it performs A value. It performs the addition operation by taking the multiplicand value and A value. So if Q0 is 1, then it will perform the addition operation. So addition operation of what? Multiplicand and whatever value is there in the register A, and the result again it stores in the register A. So this is how the sequential circuit multiplier works. So and it has a control sequencer to check whether the multiplier bit value is 0 or not. So if it is 0, it performs no add and it will perform a shift operation. So if it is addition, it will add m value, the multiplicand value will be added with the a value, and after adding it will shift right 1 bit position. So all these will be done by using this circuit. So this is nothing but sequential circuit multiplier. So we'll see how exactly this algorithm works. Registers A and Q combine, which holds the partial product, while the multiplier bit Qi generates the sequential add or no add operation. The carry out from the adder is stored in a flip-flop circuit C. The procedure for multiplication. Step 1. Multiplier is loaded into register Q. Multiplicand is loaded into register M. And C and A are clear to 0. So initially C is nothing but for carry out. So carry will be carry and register A are initially set to 0. So next in the next step we will check Q0 value from the multiplier. If Q0 is 1, add M to A and store sum in the register A. Then carry and register A and multiplier registers are shifted right 1 bit position. Means first we need to perform addition operation. After addition operation we need to store the results in the register A. Then we need to shift carry, then register A, multiplier register Q. So all these bits we need to shift one. We need to perform a right shift for of 1 bit. If Q0 is 0, if Q0 the multiplier value is 0, then no addition is performed, but whatever the value the carry, register A, register Q are holding, those values will be shifted right 1 bit position. Means no addition operation will be performed, but we will be shifting 1 bit to the right side. So after n cycles, the high order half of the product is held in register A and the low order half is held in register Q. So the final product you will be getting by combining the values whatever is there in the A and Q. So that is the product of the multiplication operation. So now we'll take one example. So here we are taking multiplicand as 13 and multiplier is 11. So we'll convert this into binary format. So first in the register M we will store the multiplicand value, and register Q we will store the multiplier value. Okay, Q will be holding multiplier value. Initially the carry register and register A will be holding value zeros. So we are initializing with 0. So this is a initial configuration. So all these are nothing but a initial configuration. So you have to initialize carry and A register value 0 and register M with the value multiplicand value, then Q with the multiplier value. So then in the step 1, so what we need to check? We need to check the Q0 value, whether it is 0 or 1. So in this operation it is 1. So if it is 1, what we need to do? If Q0 is 1, then add multiplicand value with the register value A. So here multiplicand is 1101 and register A value initially it is 0. So when you add this you will get 1101. So that you will be writing the result, you will write it in a register A. So now register A value is modified. Okay, so then multiplier value we will copy as it is. So whatever is there, so you will take as it is. Okay, so now addition operation is performed. So next what we need to do, we need to do a shift operation. Add, then shift to the right bit. So here first we'll carry a bit, we will shift it to right position. Then from the register A, one by one we will shift it to right side, one bit position. See, like this you need to shift. So now register Q value is shifted. So the last value in the Q0, that is 1, which is in red color, so that becomes a carry out bit, so that will be ignored. Okay, so this is nothing but a shift right operation. So addition and shift operation, it combines, will give you the partial product for the first stage. So this is nothing but the first cycle. Okay, so from the first cycle, the partial product what we got is nothing but the 4 bit from the register A and 4 bit from the register Q. So this becomes your partial product. So now same method, we'll check the Q0 value in the partial product from the first cycle. If the value is 1, then same, Q0 is 1, then add M plus A. So now here A value is got changed, right? So A value, what is it in the A register? 0, 1, 1, 0. Add those two. So what you will get here? You will get a carry out. Okay, you are getting a carry out. So you have to modify the carry value. Okay, that becomes 1 now, and remaining you write it as in the register A. Okay, then Q value same, whatever is there in the previous stage, so you have to write it same. Now you need to perform a shift operation. So shift 1 bit to the right side. So carry bit is done. Now we are doing a from the register A. So you have to shift 1 bit to the right side. Okay, so now register Q, that is nothing but a multiplier. Now the one which is in red color, so that becomes a carry out and it will be ignored. Okay, so now add and shift operation is done. So it forms the second cycle, and from the second cycle, what is the partial product? 1, 0, 0, 1 and 1, 1, 1, 0. So in the next step now, again check Q0 value. So Q0 value is what? 0. So Q0 is 0 means no addition operation, means no need to do a M plus A. So then what we need to do? So we need to do a shift operation. So same like previous stage what we have done, just we need to shift right side. Okay, so whatever value is there, you need to shift. Okay, so now we have shifted to the right side and we got our partial product. So this gives the third cycle partial product. So what is the third cycle partial product? 0, 1, 0, 0, 1, 1, 1, 1. So third cycle is done. Now again check the Q0. So here Q0 is 1. Then you have to add M plus A. So you will get the result 1, 0, 0, 0, 1. So carry value becomes 1. Then you write the remaining values in the register A, and Q value same, you will take it down. So now you do the shift operation. When I do a shift operation, you will get this results as the partial product. So this is your fourth cycle. So we are using a 4-bit numbers, right? So 4 stages of multiplication will be done. Okay, so here what is the product from this multiplication operation? The high order bits from the register A and low order bits from the register Q. So this becomes your product for the multiplication operation. Okay, so this is the product. So when you convert this into decimal value, you will get the answer as 143. So this is a sequential multiplication for positive number. Okay, so this method is invented to overcome the drawback of combinatorial array multipliers. Okay, so here those array multipliers, it is reduced. The combinational gates, logic gates used in this sequential multiplication, it is reduced. So it is efficient than the combinatorial array multipliers. So one more example we'll take here. So that is 10 into 10. So same method. So what we need to initialize? So we need to initialize carry and a value as 0, and this is the multiplicand value and this is the multiplier value. We need to check the Q0 value. So Q0 value is 0 here. So 0 means no add. So you will take the same value down 0 and all a is 0, and you take down the, consider the same multiplier value, and you have to shift one bit. Okay, so when you shift this one bit, you will get this as the partial product from the first cycle. Then the next cycle, check the Q value, Q0 value, it is 1. 1 means you have to add. So you have to add m value with the a value. So a all values are 0. So you will get 1 0 1 0. Okay, so then what you have to do, you have to take the multiplier same value, then shift one bit. So you will get this as a partial product. Next, check this value. Okay, so it is 0. 0 means no add, but you have to shift to the right side. So you will get this as your partial product. That is your third cycle. Then again check Q value, it is 1. So 1 means you have to add m plus a. Okay, so m plus a, and store the results in the a value and shift one bit position. So you will get this as your product for this what multiplier. Multiplicand value is 10 for the multiplier value q, that is 10 into 10, you will get it as 100. So the product is nothing but 100, which is in the binary format. So this is how we need to do a sequential multiplication. Okay. So next topic we'll discuss signed multiplication. So multiplication algorithms for the signed number. So whatever we discussed till now, it is for multiplication for unsigned numbers, and it is only works for the positive numbers. Thank you.